Hello everyone. So in this video I'm going to talk about a topic called per unit system. So per unit system is the topic. Now this is an important mathematical tool that is used in power system analysis. So it's basically a mathematical uh, trick which will help you solving difficult circuits in a easy way, where we have multiple voltage levels, we have different rating machines. It also gives you an intuition, and it also gives you an understanding. So first, let me explain what is per unit system, and then we will try to solve some problems, and then finally I will try to summarize. What are the benefits of using a per unit system. Now, per unit system, uh, if you see a similar word, you might know what is as percent system. So percentage system. So per cent means 100, per means for every 100. So for example, if you have 30% or you have 45% or 99%, whatever. So this is out of 100 what it is. So what is the benefit of having a percent? Because every time you are comparing with 100%, you are able to relatively compare the things. So for example, these are all, let's say, the amount of marks a student has scored. So definitely student who has scored 99% is having more marks compared to the student who has scored only 30%. You are able to compare the students because you know that the maximum marks is 100, because this is stated as a percentage. So similar thing happens in the power systems also. When you want to rate the machines, you have generators, you have transformers, you have transmission lines, and you have motors or various whatever is the equipment, loads. All this electrical equipment can be represented in per unit. So while percent means out of 100, so per unit means out of 1. So you're considering or one or out of base actually. So it's a called a base quantity. So let me now go into the further detail. So we have in power systems we have voltage, and we have current, and we have complex power, that is in AC system, and we have impedance. So all these four are actually complex numbers. You have seen that several times. Whenever you are talking about AC, voltage, current, power, and impedance, they are all uh, complex quantities. So let's take actual values. This is an example. So let's say the actual voltage is, let's say, 131 kilovolts at an angle of 30 degrees. So this is 131,000 volts or 131 kilovolts at an angle of 30 degrees. Now let's say current may be 5.4 amperes at an angle of minus 25 degrees. So again, this is a complex number. Now the power, I can say active power and reactive power. Let's say 50 kilowatts and plus J 70 kVAR. So this could be a load or it could be a generator. So just consider it as a load. So there is a certain load which is 50 kilowatts active power it is consuming, and 70 kilo kVAR so reactive power it is consuming. And similarly impedance, let's take something like 10 plus J6 ohms. So these are all actual values. Now I want to compare this with some kind of a base system. Then what will be the comparison values? So the four electrical parameters, voltage, current, complex power, and impedance, I want to compare with some reference. Okay, so whether this voltage is more or less, or what is the comparison? So for that we will have to define the base quantities. So base quantities. Now, the actual values are actually complex numbers. You will have a magnitude and angle, but then the base quantities are actually real numbers. So this is because we are just want to we are just want to represent the magnitude. We don't want to change the angles. We want to just only manipulate the magnitudes in terms of calculating the per unit quantities. Okay, so what are the base quantities? Now, base quantities you can choose as you wish. So let's say the voltage I'm choosing as something like 120 kilovolts at an angle of 0 degrees. In fact, we should not mention any angle here. These are all just real numbers. Now, why I chosen only 120 kilovolts? Why not 100 kilovolts? Why not 80 kilovolts or whatever value? You can choose any voltage as your base kV as per your suitability with your the problem that you're solving. So sometimes the value which is closer to the given value will be more easier for calculations. Now, what about the base current? Now, base current, I can choose some value. Before I choose the base current, first let me choose the base complex power. Let's define base complex power as 100 kilowatts. Now, there is no reactive power again. As I said, this is just a complex number. It's just a real number, sorry. Now, whenever you define, so this is let me write it as V base. V base is 120 kV, and S base is 100 kilowatts. This is what I have defined here. So two base quantities you define. The other two base quantities you will have to calculate from these two. See, you are flexible. You are free to choose any value for voltage, any value for complex power. But once you define two values, the other two values will get defined. So how? So I base current will be nothing but V base by, I'm sorry, S base by V base. Because S is nothing but V into I. So to maintain that relation, we'll have to do that. So what about V base into I base conjugate? And as I said, these are all real numbers, so we don't worry about defining it as a conjugate. So let me calculate this. So S base is 100 kilowatts divided by 120 kilovolts. So kilo will get cancelled. Watts by volts is actually amperes, and then 100 by 120. So let me go to the calculator. So 100, or let me write it here itself. 100 divided by 120. So I get 0.833. So the base current is 0.833 amperes. Okay. So what about the base impedance? So Z base is nothing but V base by I base. So because I into Z is V, so this is what I can do it. So 120 kilovolts divided by 0.833 amperes. By the way, it is okay. Let's do that. We need to be careful with the units. So 120 kilo, so 1000 divided by the current is 0.833. So I'm getting 1.44 into 10 to the power of 5. So this is my base impedance, or I can write it 0.144 mega ohms. So whatever, you should be careful about the uh, units. So let me just write down that here. So the current base is 0.833 amperes, and then the impedance base is 0.144 mega ohms. Just be careful with the units. So I have one column of actual values and I have one column of base quantities. So therefore, to calculate the per unit, just divide the actual values by base quantity. So per unit value is nothing but actual divided by base. So once you choose the system of base quantities, you divide by actual, you'll get it. So therefore, I have voltage, I have current, I have power, and I have impedance. So for each case, I will do actual by base. So so the actual is 131 kV and base is 120 kV. So if I do that, 131 kilovolts divided by 120 kilovolts. So the kilovolts units will cancel each other. So 131 divided by 120, 1.0917. So 1.0917 per unit. So this is the per unit quantity of the voltage that we are having. What about the current? So current, here I had mentioned the current is 5.4. By the way, what do you do with this angle? So angle simply continues. So the angle was here 30 degrees. The same 30 degrees will come here. So the angle doesn't get changed. Only the magnitude gets changed, converted into per unit, and it's a unitless quantity. So 5.4 minus 25 degrees. So 5.4 amperes angle minus 25 degrees divided by 0.833 amperes. So again I'll get the current in per unit. 5.4 divided by 0.833. So 6.48 per unit angle minus 25 degrees. So this is the current. Now in the case of power, I can directly divide. So I have 50 kilowatt plus J70 kVAR. So 50 plus J70. So this whole thing divided by 100. So this is kVA and this is kilowatt. So kilowatts, everything units will cancel each other. And this one will be zero point 0.5 plus J zero point 0.7 per unit. So this is how you represent the power in the base quantity. Finally, last I like to do the impedance. So I am assuming 10 plus J6. So 10 plus J6. So divided by 0.144 into 10 power 6 ohms. So this is also ohms. So it gets cancelled each other. So 10 divided by 0.144. This is the resistance part. And then 6 divided by 0.144. This is the reactance. 69.4 and 41.6. So into 10 power minus 6 will be there. This is in per unit. So this way I am able to convert the 4 electrical quantities into per unit. So this is our final answer. So this is per unit quantities. Okay, so far I have just explained what is per unit system in electrical engineering. There are 4 quantities. If you have actual values, you define base quantities. You define 2 base quantities. The other 2 quantities gets defined automatically, and then you calculate this way. So this is also an important formula. That is, per unit value will be actual value divided by base value. So these two will have same units. So units will cancel out each other, and we get everything in per unit values. Let's do 1 or 2 problems, and slowly we'll try to understand what is the significance, importance of this per unit system. See you in the another video. Let's continue our study on per unit quantities. And on your screen, now you're seeing a question. Calculate the per unit quantities of the following, taking 100 volts and 20 amperes as the base. So a base system is given to you, that is 100 volts and 20 amperes. So voltage base is given and the current base is given. So let's begin by, this is base quantities. So V base is given and I base is given. So 100 volts and 20 amperes. 100 volts and 20 amperes. The moment 2 base quantities are defined, the other 2 base quantities will get automatically defined. So what is Z base? So since V base is nothing but I base into Z base, so from this I can find what is the Z base. This is just a simple Ohm's law. So Z base will be V base divided by I base, that is 100 volts by 20 amperes. So we get about 5 ohms. This is the base impedance. So every other impedance I will compare with reference to this base impedance. Similarly, S base. This is the base for complex power. So nothing but V base into I base. So that is 100 volts into 20 amperes. So I'll get 2000 volt amperes, or I could say 2 kVA. So 2 kVA is the base complex power. So now all four base quantities are defined, that is voltage, current, impedance and power. So I can now solve this problem. So calculate the per unit quantities of the following. So 130 volts at angle of 20 degrees. So the base is anyway 100. So I can just, so depending on what is the quantity, since this is a voltage, I'll divide the actual value by base value. So actual value is 130, base value is 100. So I'll get 1.3 angle 20 degrees. This is in per unit. So this way I have converted the actual value. So this is the actual value and this is the per unit value. Okay, now I have 30 amperes. So I take the base current of 20. So 30 amperes divided by 20 amperes. So that is 3 by 2. So let me quickly calculate 3 by 2, that is 1.5. So 1.5 and angle is 0 degrees not given. So this is in per unit. Since the angle is not given, I'm assuming 0. Now I have the complex power. This is already in kVA. So to convert to base, so 5.4 plus J 6.2 divided by 2 kVA. So this is given actual value. This is the base quantity. 2 kVA we just calculated here. So that I am dividing with the 2. So 5.4 by 2 and 6.2 by 2. So this is 2.7 plus J 3.1. This is in per unit. So this is the complex power expressed in per unit. Now I have an impedance 21 plus J 15. So I already calculated the base impedance, that is 5 ohms. So 21 plus J 15 divided by 5. So 21 by 5, I think it is 4.2 and 15 by 5 is 3. So this is in per unit. You notice that entire on the right side there are no units. If I just tell you 4.2 plus J3, you don't know whether it is impedance or it is power or current or whatever. So you have to specify the impedance is 4.2 plus J3.0 per unit and so on, something like that. Okay, let's come here. So 4 kilowatts at 0.8 power factor lag. Okay, now I want to know what is the per unit representation of this. So 4 kilowatt divided by 2 kVA. So kilowatts kVA here you can actually cancel out, and this will be 2.0 per unit at 0.8 power factor lag. So this is the complex power 2 per unit at 0.8 power factor lag. Now using this 0.8, I can actually split the per unit power into both kilowatts and kVAR also. Anyway, so with this I have calculated, this is all per unit calculations I have done. Let's look at one more problem where the per unit values are given and you have to calculate the actual values. So let's go down. I have already written the problem. So calculate the actual quantities if base impedance is 10 ohms and voltage base is 300 volts, and these are the values that are given. So let's Z base given is 10 ohms and voltage base given is 300 volts. Now any two base quantities will be given, the other two base quantities I can calculate. So how to calculate I base? So V by Z. So 300 volts divided by 10 ohms. So I'll get 30 amperes as my base current. And what is the S base? So S base I can do V square by V base square by Z base. So if I don't want to use this, so this is again I'm sorry, I think this is, let me just derive it quickly. So we know that S base is V base into I base, but I base itself is V base by Z base. So therefore V base square by Z base. Yeah, I think this is correct. So what is V base? 300 volts square divided by Z base, that is 10 ohms. So this will be this divided by 10. So this I'll get 9000 volt amperes or 9 kilovolt amperes. So I have calculated all base quantities. So I have one, two, three, four base quantities with me. So now I can answer any problem. Okay, first one is impedance of zero point 0.8 plus j zero point 0.9 per unit. So the per unit value is given. I want to calculate the actual value. So since it is mentioned that it is impedance, so I will use the base impedance. So what is the formula we are using here? So the formula we are using is actual is equal to per unit into base quantity. So the per unit quantity is first one zero point 0.8 plus j zero point 0.9, and this I'll multiply by the base impedance, that is 10 ohms. So then I'll get 8 plus j 9 ohms. So this is the A part. Let's do the B part. Voltage of 0.92 degrees. Okay. So V actual equal to zero point 0.9 at 2 degrees multiplied by 300 volts, because our base voltage is 300 volts. So how much is this? 270 angle 2 degrees. So this way I can calculate the base voltage. Now current of 1.4 per unit, and the angle is not given. Anyway, I can just calculate it. So the C part, what is the base current? 30 amperes I am getting. So C part, I actual equal to 1.4 into 30. So 1.4 into 30, you get 42 amperes. And then complex power of 2.2 per unit at 0.8 lag. So S actual will be 2.2 per unit into, I got 9 kVA as my base, so into 9 kVA. So how much you will get? So 2.2 into 9. So this will be 19.8 kilovolt ampere at 0 0.8 power factor lag. So the power factor information will just continue as it is. Now if I multiply with zero point 0.8, I'll get the actual kilowatts and so on. I can always split this kVA into actual and active and reactive parts. So this way we are able to do that. So far what we have learned is what is, so you have, let me just summarize it in the form of a small picture. So you have actual quantity, and then you can go into per unit quantity. So for this you need to divide by base quantity, and if you want to come reverse, that is from per unit to actual, you say multiply by base quantity. And how is the base quantity itself calculated? So what are the quantities? We have voltage, current, power and impedance. So if you choose two base quantities, so this is V base, I base, S base and Z base. If you choose any two quantities, the other two you can calculate, and then any actual quantity is given to you, I can take it to per unit. Any per unit quantity you, I can take it to actual. This is the procedure part, but then what is the concept? Why we should, what is the benefit of doing this per unit system? Okay, so let's discuss that in the further videos. Thank you. Okay, let's continue our study on per unit systems. So far I have just mechanically explained you what is the process, but here this is one example problem through which you will really understand the benefit of what is the per unit system. How per unit system will help you in better understanding the power system equipments. So the question is like this: the ratings of a four cables A, B, C, D are given below. Determine which cable is most efficient. So what do you mean by most efficient? When the cable is operating under the rated conditions, which cable has the least losses, or which cable is the most efficient cable? So how do you determine? So you look at this, you say, hey, the cable A is having least resistance, so therefore cable A is most efficient. But then when you again look at the voltage and current ratings, you'll notice that cable B is having higher voltage rating. So since higher voltage ratings may result in lesser losses, so maybe cable B is more efficient. So just take a time. You can pause this video. You can look at the four cables ratings and try to find out which cable A, B, C, or D is the most efficient cable in this particular case. So once you have the answer, whether it may be A, B, C, or D, you can match it with my answer. Okay, so I'll answer this question now. So how do I answer this question? So in order to answer this question, I'll try to use Excel sheet. So let me just bring in Excel. So I'll simply copy the data. So I have four cables, that is A, B, C, and D, and the cables voltage ratings are as follows: 210 volts, and this one is cable B is 500 volts, cable C voltage rating is 330 volts, and cable D voltage rating is 1000 volts. And then I have I rating. So the current ratings respectively are 70 amperes and 100 amperes and 40 amperes and again 100 amperes. And then the resistance of this. So what is the resistance? So 1 ohm, 1.5 ohm, and 2 ohms, and then 3.5 ohms. So which cable is most efficient? This is what we'll have to calculate now. So in order to do that, first I will say output power, P output. So what is the output power under rated conditions? So it is delivering 210 amperes, 70 amperes at 210 volts. So simply the output power, I'll just multiply these two figures. So I interpret the ratings as this is the supply, how much the current the cable can supply and how much voltage the cable can operate under. So the output is 14700 or 14700 watts. So this output is in watts. Let me write the units also. So this is in volts and this is in amperes. So similarly, I can calculate the wattage rating of each cable. So once I have the output, whenever current flows in a resistance, there will be a losses. So let me write the losses also in terms of watts. So what are the losses? So this is 70 square. So I square into R. So 70 square into resistance is 1. So 4900 watts is the loss in the first cable when it is carrying the rated current in and the rated voltage. Now I have output and I have losses. So I can just find out the percentage losses. So what are the percentage losses? Simply losses divided by the total output. So once I have this, so let me just format it as two decimal places or whatever. So once I have this, now you see uh, losses are least for cable C. 24% is the losses, remaining power will be the output. So in fact, losses should not be calculated like this. I think this should be counted as P in. So the when the input power, so by the time the power reaches to the source, so 1470 4900 will be losses and remaining will be output, and losses calculation will be loss divided by, so output by input is efficiency and loss by input is losses. So anyway, so this is my losses. So only after doing all these calculations, I am able to conclude that C is most efficient. However, when you look at cable D, it is able to carry more power, like 100,000 watts of power it is able to carry. But then even though it is able to carry more power, it's not efficient. So under efficiency conditions, C is the most efficient. Now, what is the how is it related to per unit? So simple. Assume that the voltage rating itself is the V base. So V base for first cable is nothing but 210, and the current base I base is nothing but this one. So from that I'll get the resistance base or R base or impedance base. So simply I divide by voltage by current. So 3 ohms is the base resistance. So for the first cable, 5 ohms, 8.25 ohms, and 10 ohms. These are all the base quantities for the individual cables. So, how do I get 10 ohms as a base? If I assume 100,000 volts as the 1000 volts as a voltage rating, base voltage, and 100 amperes as the base current, then the base impedance will be 10 ohms. And once I have this base, what is the resistance in per unit? So actual resistance divided by base resistance will be the per unit resistance. So this and divided by this. So I'm getting this value. So again, let me adjust the decimals. Now you notice that the R per unit is nothing but percentage losses. So when you calculate the per unit impedance of any equipment, indirectly you will know what are the per unit losses in that equipment. So if it's a resistance element and you see 0.24 is the per unit ohms or the per unit resistance of that particular cable C, so therefore it will cause 24% losses. So just looking at the per unit, you don't need to calculate the output, input, whatever losses, everything. Just simply calculate the per unit quantity and that will give you a sense, an indication of which is the most efficient. So the new thing that you learned is uh, per unit resistance is nothing but percentage losses. So under, see, when operating under rated conditions. So of course the rating is 40 amperes. Instead of 40 amperes, if I send 50 amperes, of course the power losses will be more than 24%. That's a different thing. We are assuming everything is operating under rated conditions. Under that conditions, the per unit resistance is nothing but the percentage losses. So this is a one practical advantage or benefit of calculating the per unit resistance. So let me just so percentage losses is equal to per unit resistance. In fact, let me just, for the sake of completeness, let me write the R base. What is R base here? So 210 by 70, that is 3 ohms, and then 5 by 100, that is 5 ohms. So this is in ohms, and 310 by 40, that is 8.25, and finally this will be 10 ohms. So once I have the base, so then I'll say R per unit, which is nothing but percentage losses. So how to get per unit? 1 by 3.33, 1.5 by 5.3. Is that so? Yeah. So 2 by 8.25, this is 0.24, and finally this one will be 0.35. So the most efficient is the C. C is most efficient. So this is the one practical use of calculating the per unit quantities. Okay, so let's continue our study of per unit quantities. Now I have mentioned that per unit system. The once you have this four, so let me just do that explanation here. You have a per unit system. What do you mean by per unit system? So it will contain an S base, it will contain a V base, it will contain an I base, and it will contain a Z base. Once you have this per unit system defined, uh, any actual quantity, so this is actual quantity. So maybe V, I, and then S and Z. So these actual quantities can be transformed into per unit quantities. Then you can do the calculation here, and whatever results you get, that you can again get it back to the actual quantity. What if there is another set of per unit system? So per unit system number two. This is per unit system number one. So SB1, VB1, IB1, and ZB1. So a second per unit system may have a different value of SB2. It will have a different value of V base 2, different value of I base 2, and different value of Z base 2. Of course, these together should be consistent again. So if I define S and V, then this IB2 will be defined and ZB2 will be defined according to the other two. Now also, if the actual quantities, if I convert into per unit system and do the calculation and again get back to the solution to the actual quantity, I'll get the same answer. So irrespective of whichever per unit system you choose, the calculations and the results will be matching after converting back into actual quantity. So you know how to calculate actual to per unit system. Now how to do transformation between two per unit systems is what we'd like to check now. So there's a simple formula I would like to derive. So the formula is something like this. So Z per unit equal to, let me just, otherwise I'll just write down the question and then we'll try to solve the question, then we'll be able to do that. Let's continue it in the next video after I write the question. Okay, so this is the question where we are able to convert the per unit impedances from one system to the another system and so on. So let's look at the question first. An impedance of 5 minus J3 ohms is given. Express the above impedance in three different per unit systems as given below. A per unit system 1, S base is 100 volt amperes and V base is 100 volts. Whereas per unit system 2 will have these quantities 70 volt ampere, 50 volts, and per unit system is 3 kVA. Notice the unit K, and then voltage base is 200 volts. So how can the same impedance be represented in three different? You can do that because for each of this you can calculate the base impedance and then you can do that. In other words, if I draw it pictorially, it will look something like this. So per unit system 1, then I have per unit system 2, and let's say I have per unit system 3. So this is 100 volt ampere and 100 volts. This is 70 volt amperes and 50 volts, and this is 3 kilovolt amperes and 200 volts. I'm just copying whatever I had written before. Now the actual impedance is how much? 5 plus j 5 minus j 3 ohms. So this is the Z actual. So I can convert it into this, I can convert it into this, or I can convert into this. So let's do that for the first case. So what is the Z base here? So Z base will be nothing but S base square, sorry, V base square divided by S base. So remember, Z base is nothing but, you know that Z base is nothing but V base into I base. And what is I base? So I base is nothing but S base by V base. So this is nothing but V base square by S base. So, so Z base can be calculated like this. So here, if I do V base square, that is 100 square divided by 100. So this will be 100 ohms. So therefore, now I have calculated the base quantity ohms. So I can define Z per unit here. Z per unit 1 equal to, so this is 5 minus J3 divided by 100. So I'll get 0.05 minus J 0.03. This is my per unit impedance. So this line, any element having this characteristics, when it carries, the losses will be 5%. You can learn that from the previous video. If the R is 0.05 per unit, if rated current and rated voltage are flowing, then 5% will be the losses in this particular cable. Okay, so that's a different issue. So let's come to this. Now I can repeat the same process, but there is a more cleaner way of doing it. So here I'll attach subscript 1. So that is Z base 1 equal to V base 1 square by S base 1. And if I have a different base, so different system, then I can write like this. So let's keep these two as two equations. Now let's say there is an actual impedance. So the actual impedance will be per unit impedance 1 into Z base 1. So the actual impedance will be the per unit impedance multiplied with the base quantity. That is also equal to Z per unit 2 into Z base 2. So I can express either in base quantities of system 1, or I can express in system 2. But these two are actually equal. So the actual quantity is outside the per unit system. So these two are equal. So if I equate this and then think of ZPU2 as unknown. So ZPU2 is unknown. Then this ZPU2 will be equal to ZPU1 multiplied by Z base 1 by Z base 2. Now if I substitute this A and B into this equation, I'll get ZPU2 is equal to ZPU1 multiplied by Z base 1 will be VB1 square by SB1 multiplied by 1 by Z base will be SB2 by VB2 square. So if I simply rearrange this, I'll get something like this. Z per unit 2 is equal to Z per unit 1 VB1 by VB2 whole square multiplied by SB2 by SB1. So just rearrangement of this. So this is very important formula. You'll have to know how to derive it whenever it is required. So if I know all the things on the right side, I can find out the Z per unit 2. So let's go up. So what is ZPU2 here in this case? I need not do work on that. I can directly say ZPU2 is equal to. So ZPU1 is this. That is 0.05 minus J 0.03. Okay, and VB1 by VB2 whole square. So what was the base for the first system? 100 volts. Base for the second system is 50 volts. So 100 by 50 whole square. Then SB2 by SB1. So what is the S base for the second system? 70, and here it is 100. So this is multiplied by 70 by 100. So this calculation will directly give me Z per unit 2. So let's do that. So I have, okay, 100 by 50 square, 100 divided by 50 whole square multiplied by 70 by 100. So this is the factor, and then this I will multiply with my original per unit, that is 0.05 minus I, or 0.03 I. I'm just defining it as a complex number. So I'm getting 0.14 minus 0.084. So this is in per unit. So this way, given any per unit system, I can just transfer it and then I can find out what is the value. So for this Z per unit, just by generalization, Z per unit 3 will be Z per unit 1 multiplied by, I'm sorry, first V base 1 by V base 3 whole square into S base 3 by S base 1. So this is the calculation I like to do. So I have everything. So just I have to change the certain quantities. So what are the base quantities for third system? 200 volts and 3 kVA. So let me just go back. In the same, instead of 50 volts, it is 200 volts, and then instead of 70, it is 3 kVA. So that is 3000. So I'm getting 0.375, 0.375 minus J 0.225. All right, so this is how, given three different systems, how you can transfer the per unit impedance from one system to the other system and all. Or I can actually, actual value can be individually transferred to individual per unit system, but then using this formula you can do it faster and more better way. So I hope you learned something more about per unit system. So let's actually solve a problem and then see, in that problem we'll consider some transformers and all. How the per unit system will help. Like we'll solve the same problem with per unit system and without per unit system. And you'll notice that in the case where the per unit system is used, slightly it is easier to calculate. Let's continue our study on this topic in further videos. Thank you. Okay, so this is another problem. I hope again you will find this problem to be interesting. Let's look at the question that is there on the screen. A 150 kVA, a 150 kVA 300 by 1800 volt transformer has an impedance of 2 plus J5 ohms, referred to the high voltage side. Determine the per unit impedance of the transformer, referred to high voltage side, and referred to low voltage side. So suddenly a transformer is given to you. So far we were only working with impedances, but now we'll have to work with a transformer. So it helps to just draw the transformer. So let me simply draw the transformer. So you all know transformer will have primary winding and the secondary winding, and the rating is 150 kVA. So the rating of this transformer is 150 kVA. All right, that's good. Then 300 by 1800 volts. So the primary side appears to be 300 volts and the secondary side appears to be 1800 volts. That is basically it's a step up transformer. So if you actually calculate, it is 1:6. turns ratio. So this is high voltage side, this is low voltage side. Has impedance of 2 plus J5 referred to the high voltage side. So here 2 plus J5. This is the entire impedance of the transformer, even the primary side impedance transferred to the secondary side. And then if you know the notation, this is Z02. The impedance of the both windings referred to the high voltage side is 2 plus J5. Now the question is determining the per unit impedance of the transformer. So for calculating per unit impedance, so this is in ohms, I need to know what is the voltage base and the impedance base and S base and so on. Now look at this, 150 kVA is the rating of the transformer. It's a typical practice whenever you are dealing with the power system equipment, the rating itself will be considered as the S base. So, so therefore for our analysis, S base will be nothing but 150 kVA. Now the voltages. So what is the voltage base? So because wherever there is a transformer, you have two different voltage levels. So I separate my entire power system into two voltage levels. So that means I just identify this as region 1, region number 1, and I'll identify the other one as region number 2. So inside the region 1, I define my base voltage, and inside the region 2, so here the base voltage will be 300 volts. Why I am taking 300 volts? Again, because the rating voltage is 300, the rated is 300, I'll take the same voltage as the rated voltage. Consequently, the voltage base in the region 1 will be, since it's the ratio 1 is to 6, so 300 into 6, 1800 will be the voltage base in the second. So, but the S base will apply both sides. All regions will have a common S base because it's a transformer. The S will be same on both sides. So therefore, what will be my Z base here? Z base nothing but, so let me do it as a calculation. So here Z base will be nothing but V base square by S base. So that is nothing but 1800 square divided by 150 kVA. 150 kVA. So this is just V. So you should be again careful with the units. So how much will I get it? So let's go to calculator. 1800 divided by 150,000. Sorry, 1800 to the power of 2. So I'm getting 21.6 ohms. So is what is my, I'm sorry, let me. So I'm getting 21.6 ohms is my base impedance. So therefore, what will be my per unit? So Z base on HV side is 21.6 ohms, and the impedance actual referred to HV side is how much? 2 plus J5. Therefore, per unit impedance of the transformer refer to HV side. So let me say ZPU dash HV. So this will be 2 plus J5 divided by 21.6. So 2 plus 5i divided by 21.6. So I'm getting 0.092. So let me just write it neatly here. 0.09259, or I'll just round it off to 6 plus 2314. So this is my impedance referred to the primary or high voltage side of the transformer. So this part I have completed. Now I want to repeat the problem and do it in the low voltage side. But then when you look at the transformer, in the low voltage side, there's no impedance at all. So is the answer 0? So of course the answer is not 0. The equivalent impedance should be transferred from the secondary side to primary side. Then we'll have to apply the problem. So let's do that. Z actual refer to low voltage side will be Z actual refer to high voltage side divided by the transformer ratio. So 6 square, because 1 is to 6 is the ratio, we have to divide by 6 square. How do I know it is divided by 6 square? Because low voltage side the impedance will be less. So 2 plus J 5 is the impedance. This I will divide by 36. So this will be my actual impedance. So the numerator is ohms, denominator is just a number. So I'll get the actual impedance. That is, so I'm getting 0.00, I'm sorry, 0.55 plus J 138. Something like this. So this is the actual impedance of the transformer referred to the primary side. Sorry, referred to the 300 voltage side. So now if I once again redraw the diagram, so this is the impedance Z01, which is nothing but this one. I have a transformer now. On the secondary side, I don't have any impedance. So this is 300 by 1800 volts and 150 kVA transformer. So again, we have two regions here. So this is the low voltage region and this is the high voltage region. We are only interested in the low voltage region now. So what is the S base here? So S base of course is 150 kVA because this is same for both sides, whereas the V base is 300 volts. So therefore Z base will be V base square by S base. 300 square divided by 150 kVA. So again, be careful with the units. So 300 to the power of 2 divided by 150 kVA. So I'll just use 1000. So 0.6 ohms I am getting. So 0.6 ohm is the base. So what is Z per unit? So if I Z per unit on the low voltage side will be whatever is the actual impedance 0.055 plus J 0.1388. This divided by 0.6 will give me the actual impedance. So let's do that. So I have this quantity. This quantity already we had calculated. So this I will divide it by 0.6. So I'm getting 0.92593. So 0.0926 is what I'll round off plus 0.2314. So this is in per unit. So suddenly you notice one thing. When I solve the problem here, I got this solution. The exact same solution I am also getting here once again. So either you refer to the HV side or you refer to the LV side, the impedance of the transformer will be exactly same. So that is another advantage of per unit system. By introducing per unit system into the place where there are transformers, you can actually show it as a common impedance, and therefore that will simplify your solution. So I hope you learned something from this small example. Let's do more problems on this and we'll get more understanding about per unit systems. So as again said, per unit systems is a very important mathematical tool in power system analysis, and you need to be very strong with that. Any power system engineer needs to be very strong with understanding the concept behind per unit system, why it is used, and so on. Okay, let's continue.